I'd like to now share some applications of radian measure. I find them to be quite interesting myself. What I'd like to do before I help you understand all of the formulas here and the conversions to this final formula is I'd like to put it in context for you. So I've drawn a circle over here, and this is supposed to be a picture of the Earth with the north and the south poles. And here is the equator around its circumference. Here's the center of the Earth. And what we're getting ready to study is the velocity of a point. Velocity of a point that is rotating around a circular object. It could be us sitting on the Earth. Let's say we're sitting at the equator. So this is us sitting at a dot right here. And I want to know what the velocity of that point is as the Earth rotates around its axis. It's hard to draw. In other words, if there were no gravity, how fast would I shoot off the surface of the Earth because of the rotation? We're on a big merry-go-round. Try to relate this to a merry-go-round when you were a kid. I mean the kind where other kids would push you, that kind of a merry-go-round. And you had to hold on tight if you were sitting on the edge of the merry-go-round. But if you were at the center of the merry-go-round, you didn't have to hold on. You didn't have a radius that was causing this force to want to thrust you off the surface of the Earth. So this arrow is supposed to kind of go either towards you, like, out at you, or away from you, but it's hard to draw in 3 dimensions. But I want to find the velocity of that red point as a result of the Earth rotating, again, can't do this in 3 dimensions very well, around its axes. So first of all, the definition of velocity is the distance that you travel over the time that it takes you. So if it was a car, you'd be talking about the miles that you travel over the time in maybe hours. So the velocity would be so many miles per hour. Well, this is going to travel in an arc length, not a straight distance. So instead of using D, we're going to say S is the representation for the letter D here. So how far around the arc do we travel for a period of time? And then remember that the definition of S, which is that arc length, is theta times the radius. We've learned, remember, there's still time in the denominator. And now what we're going to do is we're going to take this theta over time, which is right here. So I'm at this point in this proof, if you will. The velocity of an object is found by taking its angle that it travels through over a period of time times its radius. And this theta over t is going to be called the angular velocity, designated by the Greek letter omega. This is not a lowercase w. This is a Greek letter. It's a lowercase omega is what that is. So a lowercase omega. We would replace this theta over time with that omega, and the r is still there, and we have this formula, and that is the linear velocity of a point moving around an object at an angular velocity. So revolutions per minute, revolutions per day for the Earth, revolutions per 24 hours. 1 revolution every 24 hours is how the Earth rotates. The wheels on your car rotate at so many RPMs, your engine at so many RPMs. Angular velocity is going to be in RPMs. However, we're going to have to convert that to radians per unit of time instead of revolutions. RPM, remember, stands for revolution per minute, and so we're going to go to radians per unit of time in order to do this calculation, times the radius with which that point is turning about. So let's look at our first problem. Well, actually, you know what? I'm sorry. Before I do that, I want to take the Earth problem, and I want to say that, the linear velocity of a point on the equator would be found by taking its angular velocity times the radius of the Earth. Well, the angular velocity is 1 revolution every 24 hours. That's how the Earth rotates. But in terms of an omega, and I'm going to go ahead and erase these words right here to give myself a little bit more room. I'm going to turn this word revolution, 1 revolution, and every 1 revolution around a circle, there's 2 pi radians in every 24 hours. And that's going to be my omega. The radius of the Earth is 3,960 miles. Excuse me for having to write that word miles down low. When I multiply 2 pi times 3,960, I'd love it if you would do that, hit enter, then divide by 24, you would get 1,036. And then let's talk about the units. See this 2 pi? Yes, it's radians, but remember, radians is a unitless measure. We don't write it. So we multiplied by miles, so that would be in the numerator. We divided by 24 hours. So anybody who is sitting on the equator right now, in any country that has the equator run through it, their body is moving about the circumference of the Earth at a speed of 1,036 miles per hour. Crazy, isn't it? We're going to talk about that a lot more in class when we do some more applications of that. Let's go on. The propeller of a motorboat is rotating at 130 radians per second. So that's supposed to be my propeller. What's the linear velocity of a point on the tip of the blade? So if that point were to shoot off, how fast would it go? But remember, it's going around and around and around. If the blade is 22.5 centimeters long, so we're going to call that the radius. This is going to be the 22.5 centimeters long. And then omega was given as, it's supposed to be that W, at 130 rads per second. Remember, radians is a unitless measure. I would find the linear velocity, v, that's what the capital V stands for, by taking omega times r, and in this case, omega is 130 rads per second. I won't write that word rad. Then I'll multiply it by the radius of 22.5 centimeters. And when I do that, I get an answer for this problem of 2,925 centimeters per second is how fast this point right here is moving about as that blade turns. Okay, the next problem. The sweep second hand of a watch is 15 milliliters long. So, the actual second hand, I'm going to try to draw something kind of with an arrow here. But a second hand moves around an analog face in a minute's time. The second hand, 60 seconds in a minute. So there's 1 revolution in any 1 minute for that sweep second hand. I'm going to show you by the factor label method that in any 1 revolution, there is 2 pi radians. Remember, that's called the factor label method. So I'm crossing off the word revs. So what I have then for omega here is that 2 pi radians every 1 minute for that sweep second hand. That's my omega. I want to know what the linear velocity is. It's found by taking omega times r. So omega is 2 pi radians every 1 minute. And the radius, it says the sweep second hand of the watch is 15 millimeters. So it's at the center, from the center to the edge is 15 millimeters. And when you multiply 2 pi by 15, you should get 94.2. And that's going to be in millimeters per minute are the units. Please be very careful with these. Watch this. You multiply by something in millimeters, that'll be in the numerator, and time is minutes in the denominator. A distance over a time is a speed. All right. Let's see. This Ferris wheel, 18 meters in diameter, makes 1 revolution in 3 minutes. this one revolution in 3 minutes is its angular speed. Its diameter is 18 meters, so its radius is, I hope you just called that out, 9 meters. Cut that in half. Find the speed of a seat on the rim of the Ferris wheel. So, here you are dangling on your seat on the Ferris wheel. So how fast is that going around the circumference? Now, mind you, just going pretty slow. One revolution every 3 minutes. I'm going much faster than it actually moves. At any rate, this one revolution for omega has to be converted into radian. It's one of the biggest things you can garner from this. So you could just go here and just replace 1 rev with 2 pi radians in a rev. So you have 2 pi radians in 3 minutes time. And we find the speed of that seat by taking omega times r. So again, omega is 2 pi every 3 minutes. The radius of the Ferris wheel is 9 meters. And when you multiply this all together, you should get 18.85 meters per minute is the speed of your body as you move around in the seat of this Ferris wheel. Okay, let's see. I'm just going to do a little quick on 3 times 2 is 6. Yeah, that's correct. All right, let's turn to the next problem. An engine. The flywheel of a car engine. Its diameter is 0.36 meters. So if its diameter is 0.36 meters, then cut that in half for the radius. And that radius is 0.18 meters. All right, it's revolving at an angular speed. This r/minutes typically stands for revolutions per minute. It could stand for radians per minute, but 750 RPMs is pretty, a reasonable number for this flywheel. So 750 revolutions per minute. Now, it goes through what distance does a point on the rim move in 2 seconds? Would you please remember you're going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm trying to get up to 750 in a minute. I can't. It's way too fast. And I'm trying to grow this circle so you can see that I'm going around. So this is going around 750 revolutions per minute for a total time of 2 seconds. So we've got to figure out the angle with which it passes, how many radians angle that it passes through, because I want to find out what distance does a point on the rim move in 2 seconds. So how far does that point go? So one time around, and then another time around, and another time around. If it goes 750 revolutions in a minute, and I want to look at it for just 2 seconds. So what I'm going to do is I'm going to first convert revolutions to radians. So those units will cancel out. Next, I'm going to see this word minute. In any 1 minute, there is 60 seconds. So now I get to cancel out the word minutes. And then finally, I could do this calculation. I don't know if I have this in my notes. I do not believe that I do. I'm now going to multiply that for 2 seconds because that's how long it's traveling. And when I do that, those words will cancel out. And when I'm done, look at all the words that are all canceled out. The only thing left is the unit of radians. So theta here, in terms of radians, is 157.1. Please remember that approximately once around the circle is 6.28 radians. So it goes quite a few times around the circle. But what you need to do, and I need to hustle here, this video is getting a little bit long, to find the distance around a circle it travels, you'll take theta times r, and theta is 157.1 radians. The radius is 0.18 meters, and when you multiply that together, you're going to get 28.3 meters. Lot more applications of linear velocity when we get into class.